So you should probably be mostly done with Lab 1 and just sort of testing out the corner cases right now. Hopefully that's the case. There have been a few people who have already checked off their Lab 1 in the lab session, so that's good. We'll be talking about some of the logistics for that, because I know that wasn't super clear on the handout, so we'll be clarifying that in a moment. Today, this is just going to be a recitation section. We'll go over some logistics for the lab. I'll go over the solutions for the homework assignment, and then we'll open it up for question and answer. Yeah, nothing too formal today. So first of all, jumping into the lab. Lab 1 is due tomorrow. It's due by midnight. What that means is we're going to not allow you to write or modify any of the contents of your hand-in folder after midnight tomorrow night. So make sure it's in there by then. Yes?
Tomorrow night or tonight?
Sorry, tonight. My brain is still, it hasn't caught up with me today yet. Yeah, that'll be tonight, so Friday night. And if you need to use a late day on this assignment, because we weren't clear on this yet, this is the clarification for that. If you need to use a late day, what you'll do is you'll zip your project into one file. You'll email 447 instructors, and you'll basically let us know I'm using a late day or however many. This is my file. And whatever file we receive on whichever date, that's what we're going to grade, and that's what we're going to count toward your late days. So just keep that in mind if you need to use that option. You should be going to the lab sessions and working on your lab, getting clarifications there, hopefully conversing with some of your fellow students. I know that can be really helpful. And the TAs are there to really help and answer questions outside of their normal office hours. Cool. So lab's going OK. How's the course going? Are people feeling pretty OK with the material? What's the speed like? Is it too fast? Is it too slow? Do you want more material, less material? Any rough feeling on that? Comments? Is it about right? Yeah? OK, good. OK. Any questions on Lab 1 that haven't been answered yet? Yeah?
It's real quick. We're defining overflow as being an exception. So overflow is undefined, right?
Yes. So the way we've defined overflow is it would cause an exception, and we're not asking you to worry about handling exceptions on the slot.
And with the exception of the branch delay slot thing, our output should be the same as spins, right?
It should essentially be the same. Yeah. Yeah. So that's a good way to test some different test cases on your simulator. OK. Let's take a look at homework 1. By the way, the solutions for homework 1 have been posted. I don't know if you've gotten a chance to look at those. They're on the wiki. Homework 2 has been assigned, I believe. So that's up there. And Lab 1.5 is out. Now, Lab 1.5 isn't a real lab per se. We're not going to grade you on that. It's just to get you familiarized with the framework that we'll be using for Lab 2. And Lab 2 will be coming out very shortly. We're just finalizing some last-minute changes on that. OK. OK. I'm not going to go through all of the questions. If you want me to go into more depth on anything, just feel free to let me know, and I'll elaborate on that if I can. But I just wanted to sort of give you an overview of how you would work through the solutions and what to be thinking about when you're going over these questions. So the first question was, it wasn't really that much of a question at all. We were just asking you to get used to using SPIM and XSPIM because we believe that would help you on your lab assignments. So hopefully you got acquainted with that, got used to sort of the odd interface that it has, and hopefully that's helping you with some of the test cases that you're using for your own lab assignment. Cool. So the first real question of the homework was question 2. So that's big versus little endian, right? And what we did was we gave you a 32-bit number, and we asked you to mark which bytes, what are the order of bytes in a big endian versus little endian architecture. This should have been pretty easy for the most part. I think this is pretty well covered. It was covered in the lecture, and it's also covered in the Mips manual. Basically, if you have a sequence of bytes in a number, let's just say, I'm not going to write the exact number, but let's just say you have problem 2. Let's just say you have byte. You have 1 byte here, 1 byte here, byte. And you have the bit over here is the most significant bit, and the bit over here is the least significant bit. If you have a little Endian architecture, the way that the byte ordering works is you start at the least significant bit, and you count upward toward the most significant bit. Okay, so in a little Endian architecture, a little Endian addressing mode, this might be the first byte that you're concerned with, or the 0th byte, the first byte, second, third. Big Endian architecture, or an addressing mode, is basically the opposite of that. You're starting at the most significant bit, and you're numbering the bytes going downward. So for big Endian, this would be the 0th byte, first, second, third. Hopefully that's pretty straightforward by now. Why is this important? Because as an architect, we might have to interface between different layers of storage, different layers of memory. We might want to store data in a different way that we want to manipulate it in the architecture. Or maybe the programmer wants to use data in a different form that we're manipulating it in the processor. We need to be able to translate between these different ways of naming the same bytes in a machine word. So that's that problem. Next, we looked at different types of instruction set architectures. Right? So you have the 0 address machine, 1 address machine, 2 address machine, 3 address machine. By the way, a bit of a side note. So why is the 0 address machine called a 0 address machine? Aren't you giving it an address sometimes? So what's up with 0 address? Anybody want to guess? Yeah.
The operating instruction is not taking address.
The what instruction?
The operating instruction is not taking address.
The operating instruction. Yeah, yeah. So really, these address machines are named after what do arithmetic or ALU type instructions take as their operands, not necessarily what do instructions that work with memory take, because those are going to need an address unless you have a different way of moving through memory. Cool. So let's start with the 0 address machine. So this is known as a stack-based machine because you basically just have, in your architecture, you'll have some sort of stack maybe that grows upward from the bottom here. And you're pushing values onto the stack. And when you apply an operator, you look at what values are at the beginning of the stack, apply that operator to them, and store it at the first position of the stack. This is A, this is B. If we apply some operator like plus, then this could contain A plus B, right? OK, so let's take a look at what we're doing here with our instruction code. So the program that we're trying to execute is A equals B plus C, B equals A plus C, and D equals A minus B. OK, so in a stack-based machine, what do we do first? Where do we start? Anybody? Yeah, so if we wanted to execute this instruction, what should we push onto the stack?
Push B and C.
We want to push B and C onto the stack. So let's just set here. OK, so we might want to start by pushing B and C onto the stack. Does it matter which order we push B and C onto the stack? Why doesn't it matter?
Because we're adding.
Because we're adding, right. So the order that the operands are in, it doesn't really matter for the addition. Now this might come into effect later on. OK, so once we push them onto the stack, what do? Well, we want to apply some sort of operator to these, right? So we're going to basically add. And it's implicit what we're adding because that's defined by whatever is at the front of the stack. OK, and so we can basically do similar things. Now, there's one other little subtlety here, which is in the question, we asked you to make sure that all of the contents of the variables was stored back into main memory. And so on a zero address machine, how we do that is we pop the front of the stack back into a memory address. In this case, if we were storing something into A, we would pop the head of the stack into the location A. And this is able to store it back into memory, so we can use it later on. OK, and similar thing with A plus C. So we're going to continue this code up here. We're going to push A, the A that we just stored back into memory. Going to push C. And we're going to add these together. And we're going to store them. And by store, I mean push back into the memory, or pop back into the memory, into the location B. OK. Now, the only maybe subtle part of this question was, as I mentioned before, with the subtraction operator. This one actually, the way the ISA that we gave you has defined it, depends on which order the operands are in the stack. So what did we say exactly? We said the subtraction, OK, so to compute A minus B with a stack machine, the following sequence of operations are necessary. So push the thing that's to the left of the minus sign, push the thing that's to the right of the minus sign, and subtract those two. What's to the left? A. So we're going to push A, push the thing that's to the right of the minus sign, B, and we're going to subtract. That'll give us A minus B at the top of the stack, and we'll pop that back to memory in the location D. OK. So we also gave you some rough numbers for what the size of these instructions would be, what the size of a memory location would be, an address would be, and how much data we would fetch from memory for each of these operations. So we can run through that example, but basically what you're doing, and I'll refer you to the homework solutions for the answers to these, but what we're basically doing is we're looking at, OK, first of all, there's going to be some cost for specifying which instruction we're using, like push, pop, add, subtract. That's going to be a certain cost. And I believe what we assumed in the homework was the opcode is 1 byte. OK, so that's always going to be 1 byte for this portion. Now, if we additionally specify some sort of address as an operand, that's going to be an additional 2 bytes, right? And if we're moving something to and from memory, which in a zero address machine, remember, anytime we're pushing or popping, we're moving something from memory, then that would consume 4 bytes, just to bring the value of B in from memory. So you can go through and you can add these up. We've provided a breakdown of that in the solutions. OK. So let's go on to the does this make sense, by the way, to everyone? This should be sort of just a review of what we've covered in the course and what you did in the homework already. I just want to make sure that everybody's on the same page for this going forward. Cool. So for the one address machine, basically in this case what we're doing is we actually have, so remember before our processor had this stack that was a hardware stack internal to it. Now with a one address machine, you can kind of think of the processor as having something more like a, that's right. It has more of just a little internal storage space that it's using to hold temporary values. That's a one address machine. So for example, we can load data into this little temporary space, or we can store data from it. And we can add or subtract or do whatever we need with values from this small temporary space. So for example, to do that same program, we could do something like Okay, first we're going to load the thing that's to the left of our operator into this space. So we're going to load the value for b. And then to that, we're going to add c. And the result that's now in this small little hardware storage area is what we want to store back to memory. Okay, so we can perform a store. And where are we storing it to? We're storing it back to A. OK. So you can repeat this process for the other instructions, right? It's a pretty regular way that we're manipulating this data. Now we could load A again. We could add to A C, and we could store that in B. OK. What are the main trade-offs between a 0-address machine and a 1-address machine? Can you see any trade-offs that we would have? I've shown 2 of the instructions here. We could add the 3rd one. But just based on what I have right here on the board, let's compare maybe 1 instruction to 1 instruction. What are some of the trade-offs that we as architects might consider when we're choosing an ISA for our design? Any ideas? Yeah.
Well, you do have to access memory every time you want to do something.
For which machine?
For the 1 address versus with the 0 address, at least the arithmetic operations, you don't have to access memory.
Right. So for the 0-address machine, every time we want to source an operand, we have to go all the way to memory, grab that data, bring it back to the processor, put it onto the stack. With the 1-address machine, we kind of have this little temporary space that we can hopefully use when we're in the process of executing an instruction to avoid having to go to memory as much. We can store some temporary results there. Any other differences you see? What about if we're trying to implement this? What if we're designing a chip and we want to implement one of these architectures versus another? Which one would you want to implement? Or are they both effectively the same? They're not the same, right? In the stack-based machine, you have to have some logic to manage that stack space. So even though it's a hardware-managed stack, we still need some way of, when we push something onto it, what's the head of the stack now? When we pop something, OK, what's the new head of the stack if one exists? How do we connect this to the memory so that everything is able to be stored efficiently? What about the 1-address machine? There's no pushing or popping semantics that are going on in this architecture. We just have one space, and we implicitly know what we're addressing when we're talking about this one space. It's not the head of a stack. We don't have to manage multiple entries in this. And so it could potentially be a simpler design. With the stack-based design, what if you want to push an infinite number of entries onto the stack? What if you have a recursive function that needs a lot more stack space than you can provide in your hardware? What happens then? Any ideas what you might do? Maybe you have to start storing stuff to memory. Maybe you have to worry about those conditions as well. Just something to keep in mind when you're looking at these problems. By the way, so I know that the exams are still a far way into the future, but what we as the TAs are trying to emphasize in the homework assignments, in our interactions with you, are sort of the thought process that you'll want to start going through in order to prepare yourself for answering the questions on the exams. Some of the questions will require you to sort of take a look at an architecture, think really critically about, as an architect, why would I choose one design versus another? What are the trade-offs? And we've been talking a lot about trade-offs in class. And reason about, OK, I would choose this design for these reasons, and it also has the following shortcomings. So we're going to encourage you to sort of stretch your mind a little bit, think about what are the pros and cons, and the overall goal is to hopefully prepare you for the material that you'll be seeing on the exams. Just a side note there. OK, so let's go through just a short example of the remaining address machines. So for the 2-address machine, this one was a little bit tricky, right? if you were like me when you looked at this question, you sort of said, well, how can I start with an empty value in memory that I want to load something into and then perform a computation on it? I can't assume that memory is just set to all zeros, right? We can't make those sort of assumptions. It could be random values. So in a 2-address machine, what's the way that you basically clear an entry in memory that you want to eventually store to? How do you do that? Do you remember a 2-address machine? So the way it works is we give it some sort of operand, and we give it 2 addresses. Let's call it address 1 and address 2. How would you do this?
Yeah. You would subtract the address. Well, if you want 0, you'd subtract A from A to get 0.
Yeah, you could subtract the value that's at this address from the value that's at the same address, and you end up with a nice zeroed spot in memory that you can now work with and manipulate, right? So the way that a 2-address machine typically works is you'll see something like this. You'll start off with, if we want to store into A, we'll start off by subtracting the contents in A from the contents in A. What does that mean? That means at this point, the value at A, let's just do star A, is equal to 0. Perfect. Now we have a clean slate that we can work with. And now what you can do is you can just start adding back in the things that you want to perform an operation for. So you can add back in into A, you can add B. So now the value at A is B. And to this, you can add in C, right? So you can add into A, C. And now the value at A is B plus C. And that's exactly what we were looking for. So the key thing with the 2-address machine is you first need to clear the contents of where you eventually want to store your data, and then you can go ahead and perform your operations. That's for that first instruction. For the second instruction, it's basically the same. We just have to subtract the value that's at B from the value that's at B. We get to 0. We'll add in A, add in A to the location of B, and then we can go ahead and add in C. OK. Is this making sense to everyone? OK, cool. 3-address machine, that's memory to memory. So let's start here. What type of a machine is Mips that we've been using? I heard something. Somebody want to speak up?
3-address register machine?
3-address register machine, or load store type machine, right? Because you're loading things into registers, storing them from registers. Yeah. 3-address memory to memory. This is where the operands that you give as in an instruction are actually addresses in memory that you want to manipulate. Does anybody know a modern architecture that has a memory-to-memory type operations in its ISA? So x86 actually has some instructions that will perform operations in a memory-to-memory manner. Or at least it gives the appearance that it's just going directly into memory and manipulating them. That's a bit of a side note. So let's look at this 3-address memory-to-memory machine. So life is simple when you have a 3-address memory-to-memory machine and all of your data is stored in memory, right? You can just directly modify its contents in memory by specifying addresses. So what happens here? For the first instruction, A equals B plus C, we have 3 addresses. They're all in memory. Perfect. So in a 3-address memory-to-memory machine, what we might do is something like this. Add, store the result into the location in memory given by A. One of my operands is going to be the location in memory B, and the other one is going to be the location in memory C. This will go into memory, do whatever it needs to do to give this appearance of going into memory, taking these two values that are stored in memory, summing them together, and storing them back into memory at the location of A. How about for the next line of code? B equals A plus C. B equals A plus C. All values in memory. And we have one more instruction, right? We have the subtraction instruction. What's the big difference with this type of ISA compared to the other ones that we've looked at so far? What's significantly reduced in this type of ISA? There's one component that's significantly reduced, yeah. So loads and stores, at first glance, it seems like they're potentially reduced.
In terms of the instructions?
Yes, I see what you're getting at. Yeah, so that's right. So in terms of the number of instructions that you're actually executing, this has a very small number of instructions that you need to fetch from memory and potentially, decode and do all of the stages that we're learning about in class. So this is great. Your program size is really, really small. What's a downside, though, of this type of ISA?
You're always having to access memory for every instruction.
Exactly. There's no notion of temporary storage in this type of ISA. In the zero address machine, we had the stack. That was great. We could use that when we had some sort of re-referencing of values. In the one address machine, we had this little temporary space that we could use as well. Right? For two address, again, we're still going to memory a lot there. Here, though, the main compelling draw of using this is very much reduced code size. But we don't have that benefit of what we'll learn later is called locality. So just to give you a bit of a preview of something that we'll learn in later lectures, locality is when you can actually benefit from reusing the values of certain types of data. So in the one address machine, we actually were able to benefit from the locality of some data that was provided by this small little storage space here. We could reuse values. What type of a structure in processors that we'll look at actually benefits a lot from locality? Can you think of a structure? One that we've learned of, or maybe one that you just happen to know? Any ideas? Where do we reuse values from? Registers are one example. Caches are another example that we'll talk about in a lot more depth. But we've sort of given you a high-level allusion to some of the elements that we'll be looking at later. Yeah, so it turns out that locality is a really powerful thing to take advantage of when you're designing architectures. And architects use it a lot in their designs. And we'll see more examples of this in class. OK, and so for the 3-address load store machine, you should hopefully be familiar with this by now. This is what you've basically been implementing, programming, generating test cases for the lab. But let's just run through this very quickly. So we have a register file in the 3-address load store machine. That's where we're basically storing values from memory that we want to work with. And we reference locations in that register file in the operations that we're performing. So for example, if we wanted to add B plus C and store it into A, we might first, so this is a 3-address memory, 3-address load store. So we might first load into, I don't know, R1, let's say, the value that's at B in memory. And we might load into R2 the value that's at C in memory, right? And then we can basically just perform an addition on these two values maybe stored in R3, R1, R2, right? This should hopefully be familiar by now. What's the main advantage of a 3-address load store compared to some of the other ISAs that we've looked at? It's a big advantage. Can you think of one? Are there any? Is it basically the same? What's different about it? Yeah.
You want to do it off, you don't have to go to memory.
When you do an operation, you don't have to go to memory. So it has some of the benefits of some of the other ISAs that we've seen, right? Like, for example, the zero address machine. Any other thoughts? Code size is reduced a little bit compared to some of the other ISAs because we're able to encode a lot of information into each of these instructions. We're taking 2 registers here and storing them into a 3rd register here, right? We can sort of provide the same amount of detail for the operation as in the 3-address memory-to-memory machine. Yeah?
You benefit from locality because if you want to use B or C again, you already have them.
Exactly. You benefit from locality, like we just talked about, because if you wanted to use B and C in a later instruction, they're already located in your register file. That's great. We can reuse them. What's the big downside, though, of that? This doesn't come for free, right? What did we have to do to implement this architecture? I heard somebody say register file. Yeah, we had to add this really big, really expensive, potentially, register file that we're using as storage, right? That doesn't come for free, especially when you want to consider the alternative of just this one little space in our processor where we store a little bit of data, right? Compare that to a full-blown 32-entry register file that we're storing lots of different data values in. Just some trade-offs to consider. OK. And if you work through the data transfer amounts, the instruction transfer amounts, it turns out the 3-address memory-to-memory machine, like we talked about, is the most efficient in terms of the size of the code. And the load store machine is the most efficient in terms of just total overall bandwidth, because it both has the code size benefits of the 3-address memory-to-memory machine and some of the locality benefits, so we don't have to have as many memory accesses as the other machines that we saw. Cool. OK, so the next problem, if you remember, was implementing Fibonacci of a certain index in Mips. I'm not going to go through the answer on the board right now, but I wanted to ask if there were any questions on this problem. This was just to get you acquainted with the Mips ISA if you weren't already. Were there any questions on this problem? The solution we posted basically shows you a full-blown implementation of how you would do it if it were a function call that you were issuing as part of your code. So we store the callee saved registers. We have a nice loop, and we're able to return to the address that was stored in register 31. Remember, the register 31 is the link for a jump that was performed. So we show you the full-blown way you would do that. We won't be grading you based on that full way. There's lots and lots of different ways of implementing this function. Some take less amounts of code. Some don't have to be function calls. They can just be a fragment of code. We'll be lenient when we're grading this problem. But we wanted to give you one full-blown implementation for you to sort of get a feel for. Cool. OK, and then the next component of that question was do you remember repeat, move, store, byte? From the x86 ISA, implementing that in Mips. Again, I won't be going over the assembly code for that. We have that posted online if you want to take a look. It's fairly straightforward. We basically just have a loop that's iterating through each of the different bytes that we want to move, and it copies those values over. OK, and the values that we get for what is the code size, how many instructions are executed for this register state versus this register state. This will depend on how you implemented repMoveSB. So there's different answers for that. As long as it's consistent with the answer that you provided, that's good. I think we asked you to try and minimize code size. We're not going to mark you wrong if you have an extra instruction or two. So we'll be lenient there as well. OK. On to data flow. So data flow, at a high level, can somebody describe to me what is the purpose of a data flow processor? What is it really trying to accomplish? Why couldn't we just be content with von Neumann architectures? Any thoughts on this? It's a bit of a philosophical question, I guess. Yeah.
Isn't it trying to, like with this, you're gonna waste hardware, like it's not all going to be used. So isn't it trying to exploit like sort of like natural parallelism in what you're doing?
Yeah, so I like that second part, and we'll get back to the first part in a second. Exploiting natural parallelism. Maybe natural is a bit of a, maybe we can say that it exploits all available parallelism in a program. That's really the beauty of a data flow machine, is if there's parallelism, if there's any instructions that can run concurrently with one another, that means without violating dependencies between the instructions, a data flow machine will notice that, and it will execute them in parallel. In terms of wasting hardware on this machine, it's not clear that a data flow machine necessarily requires more hardware. Here's an example. What if your program has a huge amount of parallelism? What if every instruction in your program can be executed simultaneously? How much hardware do you need? You basically need enough hardware to hold your entire program on your processor. It's really difficult to build the hardware to efficiently execute data flow type programs in a data flow architecture because you have this sort of dual-edged benefit and curse of exploiting all of that parallelism. It's hard to build machines that can actually handle that. So just an aside, some attempts of implementing data flow machines have tried to throttle how much parallelism you can have at any given point in time because you only have limited hardware resources. But now you're starting to take away some of the benefits of a data flow machine. Just something to keep in mind. OK, let's go through the data flow. Let's go through the data flow graph for Fibonacci that we have on the homework solutions. OK, so Fibonacci, what you're basically doing is you're keeping track of two numbers. Occasionally, you're summing them together. And then you're setting them equal to the previous values of the other ones. And you're continuing in an iterative fashion. That's how you build up a Fibonacci number. You keep summing values and sort of shifting them into one another's positions, and then summing them again and summing them again and summing them again until you get to the index of the Fibonacci number that you're interested in. So let's start with that indexing portion. In our data flow graph, we're going to need something that's counting down the number of steps until we're ready to halt from the problem. So one way of doing that is you could say, the user is going to give me a value n. This is the Fibonacci number they want to compute. So that's a given. N is a given. And in a data flow machine, let's start with a simple example. How would you decrement n in a data flow machine? What's the operation to subtract 1 from n? Given the nodes that we provide, which, by the way, we provide you plus, greater than, copy, and branch. How would you subtract 1 from n in this architecture? What would your node look like? What kind of node would you use?
Yeah, just add -1.
What's that?
Just add -1.
Yeah, so you could take n as one input to an addition node, and the other input could just be -1. Right? OK, that's good. But this isn't the only thing that we want to do with n, right? Because ultimately, at the end of the day, n is controlling whether we're performing the additional computations in the Fibonacci number calculation. So we need somehow to make n control some other computations that we'll perform. And those computations I'll define in a second. But for right now, just consider them to be the stuff that's really doing the number crunching for Fibonacci calculation. So in a data flow machine, how we define that some value is going to control the computation in another portion of data flow code is we use these comparison nodes. Or sorry, we use these comparison nodes and potentially copy the values to compare, to provide the output of a comparison to more nodes in the system. And I'll show you what this looks like. So for example, in the solution we have, you could take n, you could copy the value of n, and you'll see why we copy this in a minute. But we could perform the comparison here. So if n is greater than 1, if our user said I want the Fibonacci number 5, and I'm at 4 right now, I want to keep going. I want to keep computing Fibonacci numbers. So we'll take this output here, which will be some sort of Boolean value. We'll copy it, because we'll need to reuse it later on. Some of this value of do I keep going is going to go over here. We'll fill this in later. But this is where that control is really coming from. You're starting from n. You're checking, do I want to continue this algorithm? And based on the result, you're using a true result of, yes, I want to control the algorithm, to then activate all of these other nodes that are doing the actual computation, which we'll fill in. Other than that, though, on the just keeping track of the number of iterations side of things, if the value of n is greater than 1, what do we want to do? We want to decrement n. So the way we can do that is we can basically take another version, another copy of this Boolean value, and we can use that to control this branch right here. So if I want to continue my computation, if n is greater than 1, then I'll do just what you said. I'll subtract 1 from the value of n that was copied here, and that'll be my new value of n. So what this is really doing right here is it's doing the n equals n minus 1 portion of the code. Everything over here just controlling the rest of the algorithm. What this is doing right here is it's answering the question of, do I want to keep going? If so, I want to decrement it and do some other things. Sometimes in a data flow machine, we won't actually need to use all of the values from a branch instruction. In this case, if n, if we don't want to decrement n, we don't want to decrement n. We also don't want to do anything else with it. So we just set it to ground, just a notational thing. OK, so this portion of code, are you with me so far? Basically, we have something that's controlling iterations, and it's sending some signals to what's currently a black box, but which will actually perform the computation right now. Any questions so far? OK, let's fill in this black box. So from the programmer, we're given values, or from the algorithm itself, we're given some initial starting values to compute the Fibonacci number, right? We're going to need, I'm going to call them A and B. And basically, to compute the Fibonacci number, let's say n, we'll take basically C, which is the nth Fibonacci number, is B plus A. And B is the n minus 1th Fibonacci number, and A is the n minus 2th Fibonacci number. And it'll sum those together, store it in C. And when we want to compute the next one, we'll store B into C. Sorry, we'll store B into A, C into B, and we'll use those to compute the next C that we'll use. OK, so our starting values for A and B are A equals 0, B equals 1. And ultimately, what I just mentioned is that we're going to, at some point or another, add them together. Now, don't copy this down if you're doing it right now. We're going to add a little bit of extra nodes in here, but I'm just trying to show you the overall sketch of where we want to end up. Eventually, we want to add these two values together. This will produce C, our Fibonacci number for whatever iteration we're on. And if we want to continue performing computation, remember this portion of the code, if we want to continue performing computation, then maybe we'll do something interesting with C that I'll show you in a second, like, for example, store it into B. If we don't want to continue performing computation, what does this mean? We've reached a point in the program where we don't want to continue performing computation, and I'm holding the current value for C. What does that mean? That means we've reached the point where we've reached the point in the code where we've generated the Fibonacci number that the user had requested. So we actually just send this to the out signal, which is basically returning the value. What controls this branch node? We were just talking about it a lot. What controls that branch node of I still want to perform computation, or I'm done performing computation? Yeah, essentially, this check, which we've copied the signals for. So let's put one of them going here. That'll control, again, whether we're done performing the computation. OK, so we're not done yet, though, because if we want to keep going, then we need to update our values for B and A. Well, B is easy because we have C right here. And if this branch is true, keep going. This wire, or this arc right here, will contain the value of C. We can just store that back into B, just like we wanted to do here. For B, on the other hand, we want to copy its value. One of these values of B will go here into this addition node, like we had before. But what the other value will do is it'll actually go on down and potentially update the value of A, like we wanted to over here. How do we know if we want to update the value of A? How do we know? We just talked about it. Exactly. That's where we're using this comparator again. It's driving all of the decisions that we're making on the algorithm side, on basically the portion of code that's actually doing the computation. We can use this as a Boolean signal. These are Boolean signals into this branch instruction. And if we do want to keep going, then we update the value of A to the old value of B, like we did here. Otherwise, well, we don't really do anything there. At the end of the day, this will be A plus B, which will be stored in C. C's value will be stored back into B. B's value will be stored back into A. Question. How can I be ensured that when I update C, that it happens in this order? C gets updated, then C's value, or C's old value is stored in B, B's old value is stored in A, and then we perform the computation. How can I be guaranteed that it'll happen in that order? Meaning, what's preventing this whole circuit from just like, you can think of this as a circuit. What's preventing it from just sort of short-circuiting, and you have all of these different values going across all of these wires, and you don't know if the B that you're looking at was from the current iteration or the previous one that just happened to get there fast enough? What's keeping order in this data flow program? Any guesses on that? Yeah.
Just the conditionals.
The conditionals are part of it, but even those are obeying some sort of law in this machine that's preventing them from firing out of order or in some weird non-deterministic order. Yeah?
Each of the nodes has a queue, and unless the previous one is already processed, the next data is going to be queued on it. So you have A, and then if B is updated, B is queued, unless A is processed, the next value of B is processed.
Yeah. So what you're getting at is that's what's guaranteed by a data flow machine. Remember, we don't fire a node in the data flow machine unless both of its inputs are available. The way we implement that, we could use a queue for the inputs, for example. We could have just a slot of memory that has which inputs for the current instruction am I expecting. But order is maintained in this potentially chaotic system because of the way that data flow works. We won't issue an instruction until we have all of its operands. That maintains a nice order, and it lets us execute instructions that are completely independent, as many of them as we want to that the machine can satisfy. Good. Everybody clear on the data flow machine portion? Yes?
So why can't we remove the branch for A? Wouldn't we do the same thing? You don't need a decision for N to update A.
I guess so. So what would happen if we, let's see, let me think about this.
So the only difference
Right.
is right at the end when N is equal to 1, A would get updated, but it would not reduce.
Yeah, so I'll double check this and make sure that this is the case. But I think what we're doing here is we want to have the branch so that we can separate iterations of this algorithm. So this separates the old value of B from the old value of A. And when we're moving to a new iteration of the loop, then we actually satisfy this condition and copy B into A. Otherwise, B would always be the value of A, and we would be adding B to B right here. Do you see that? If this branch wasn't here, what would this look like? This copy would go right here, and we would be adding B to B. We need something in between that's kind of buffering the old value of B until we're ready to update A with that value. Does that make sense?
But if you have a queue at less node, then it will always be the right thing.
If you have a queue where?
At each of the operands of each node. So for the plus, you have a queue at A and queue at B. So it will go in order. I mean, that is the case.
If the A was it, yeah. So that could, if we assume maybe an underlying implementation where you have a queue and you can store multiple future results that you want to use, then I think that perhaps that would work. I haven't thought through that example exactly, but I think that could potentially be another solution. I think here what this problem assumed was that you can just store one value, and you won't queue up multiple values even if they could exist. Yeah. If you use that for your homework and you specified that there was a queue here, or that's fine. So, yeah.
So if present state of flow, we have like in essence some kind of ready token that flows through the system, right? Such that so when the B is ready at the very beginning, so the token flows through that copy, it sends it on both sides. So now we have B is 1 on both those, that kind of system.
Yes.
And at least the way that I was thinking about it when we explained in lecture was that we don't know how the tokens will flow through the system. We just know that they'll only flow through a node when all the input tokens are ready.
Yes.
Well, then in this model, for example, say N's 2. So So what could happen is we could have it, and the n token's copied, so now it's on both of those.
Okay.
Then we have, say, B over there, B's ready, it's copied, and then A copied, and then we execute the add to C there. So that's one possibility, and in that possibility, everything works fine.
Okay.
Right? The way that I think could also happen that would break the system is n flows. So there, it's there. If it's 2, it's greater than 1. So it continues to flow the tokens down at the greater than. We copy it, so now it's on all those. It goes over to the branch, so the branch is now true. Then we have B, propagates. Now branch is ready, it propagates again, overrides the 0 of A, becomes B. And then we have B plus B for the first C, and that's not good.
Well, but the value of C should have been already computed here and stored back to.
But isn't
where
that
B was.
assuming that the tokens have flowed in the order such that you get the 0 and the 1 sum first? Because that path through n that I described is perfect. It can do that all at once, and there's no interrupt before. Like it doesn't have to check to make sure C is ready or any kind of thing on the secondary C computation branch is ready. I don't know if I explain it well enough to try to describe what I'm saying. Like, that's an independent branch that can just flow through and end up such that if this side hasn't even executed yet, that you'll end up with an incorrect result.
You're saying it'll keep
What I'm
just.
saying is that this end counter is kind of autonomous. It can kind of do its own thing and get to a point such that when you're trying to do C calculations, it gives incorrect information to that.
I see what you're saying.
Yeah.
So this is getting back to how are we actually implementing this machine at the end of the day? Can we queue up a large number of requests, or can we say, you can't fire this node until I can store the results of this node in all of its destinations? So if I can't store the result of this node because all of its other inputs aren't ready yet, then that would effectively throttle this node from firing just asynchronously from this portion of the data flow graph. If I say, so we're kind of getting into the implementation details of the data flow architecture.
What you're saying with the queuing is that if you could queue up, or if you like, it's hard to prevent queue. Like one of the first things that I was trying to think of was, could you just have that running such that when you try to then control C, now n's like 5 and C hasn't even started yet.
Right.
If what you're saying is true, then if there's no queuing, and that when it hits that copy node, it's stuck because there's still booleans that we did the first time, then it's perfectly fine. So what I'm trying to say is that in the very first execution, if we assume that we can, as long as there's no blocking or anything, we can just execute this machine in any nodes we want as long as the token is on its inputs are ready, then you could end up with the very initial one would be going over. And that's of course assuming that we can't QA.
Right.
So you're right, if we can QAs, then I guess we're fine, but if we can't QAs, then we override the initial value.
Yeah, so I think that, so basically what we're getting at with this question is that there are a lot of, when you actually sit down and implement a data flow machine, there's a lot of considerations that you have to take into account in order to provide correct program semantics. I don't know if we'll get a chance to cover those in this course. It's good that you're bringing this up. I'm glad that you're thinking about it. But I think for right now, just assume that things will get buffered or queued however they need to allow the correct execution. And we might actually get to the point where we can discuss some of the data flow machines. If you're interested in learning more, there's one of the classes that Professor Mutlu teaches, 18742, actually goes into a lot more depth on data flow machines. And this might be interesting for you if that's the case. But right now, we're just trying to get across what are the high-level concepts of the data flow machine, how might a program look, and how would it execute. But that was a really good question. Thanks for bringing that up. OK, moving on to performance metrics. So these you really had to, I don't know if you've taken a look at the results, we'll go over, or the solutions, we'll go over them. But you really had to think and stretch your mind to answer these questions correctly. I think that's good because that's representative of what you'll be expected to do on the exams. So let's take a look at these. If a given program runs on a processor with a higher frequency, does it imply that the processor always executes more instructions per second compared to a processor with a lower frequency? When you say it back to me, you don't have to use less than 10 words. Any potential answers? What did you answer?
Not necessarily, because if you're executing more cycles, you're not guaranteed that it's the same number of instruction or cycles per instruction on two different implementations of the same ISA.
What's an example of where on one processor you might have one number of cycles per instruction, and on another processor you might have a different, much larger time?
Mips versus, what we did here with number 2, for instance.
So what we did here with the different type of address machines.
Right, yeah.
So where would the
Different ISAs, sorry.
Sure, the different ISAs. So where would the, I guess, complexity come from that would cause the number of cycles per instruction to change?
In the microarchitecture.
In the microarchitecture, yeah. So even if you take two processors that have the exact same frequency, this is a very important concept in performance, exact same frequency, you can still have the case where the processor with the higher frequency actually runs slower than the processor with the lower frequency. This is, this is very important and a fundamental concept. A long time ago, when personal computers were first being sold, there was a lot of talk about what is the frequency of the particular processor that was in this IBM PC versus this other PC versus this other PC. People looked into how many instructions per second can it process, what is its performance on these C benchmarks that people have defined. And it's all very misleading because you can't really tell just based on a metric like frequency or even instructions per second what the overall performance impact on your program will be. This is a very important concept, so keep it in mind. We'll test you on this for sure. But it's a little bit tricky, right? Because, I don't know, at least when I was growing up, and I didn't know much about computer architecture, I would just look at what is this AMD processor, what is this Intel processor, what's the frequency? Oh, well, this one is running at 4 gigahertz, this one's 3.2 gigahertz. But no, it really depends on what's going on inside of those. Yeah?
So today when we hear 3 gigahertz and all that, is that still frequency or is that instructions per second?
So anytime you have a hertz value, that'll be the frequency of the clock. They usually don't report instructions per cycle, for example, which you could use frequency to compute per second. To give you a rough ballpark, aggressive modern Intel processors might be able to execute up to 4 instructions per cycle. You might be able to fetch that many and process them. And we'll learn a bit more about what are the details of all of the steps, just to give you a rough figure on that. Yeah. OK, so Andrew was correct. Good answer. What about the next one? If a processor executes more of a given program's instructions per second, does it imply that the processor always finishes the program faster compared to a processor that executes fewer instructions per second? So now remember, we're looking at instructions per second. We're taking into account both frequency and the number of instructions that can be executed per cycle. Is this necessarily the case? Yeah?
I think I said if it's the same ISA, like if it's the same, the instructions are doing the same amount of work.
If it's the same program, if it's the exact same number of instructions and type of instructions and everything, then yes, it will be the same, but we don't necessarily know, right? We have 2 different processors. It's good that you actually predicated that because we'll take that into account, and I think that's a reasonable response. But the more general point, I guess, here is that in general, if I give you a processor and I tell you it can execute this many instructions per second, and I give you another one and I say it can execute the same instructions per second, that still doesn't tell us anything about performance. What if it's a Mips machine versus some sort of x86 or complex instruction set machine? Maybe the complex instruction set machine is actually able to represent it in a lot smaller amount of code, and it's still able to decode it fast enough and execute it. Maybe there's just less amount of work to perform. Yeah?
But when they say instructions, they mean micro-op, then it would be faster, right?
Even micro-ops could differ from ISA to ISA. Even micro-ops could differ. Micro-ops are really just a microarchitectural way of breaking down instructions, but there's no like defined set of these are the little atomic micro-operations that all processors will use. So Intel might use more complex micro-operations or break one instruction into a lot more micro-operations than maybe another ISA would. Yeah. So we can't make any assumptions about what the program is how it's actually being compiled and run. Yeah.
When they say the same program is run on two different processors, does that imply that it's using the same instructions?
No. It means that the same source code, basically, is being run. And even if it was the same binary, what if we had something like a translation layer? What if I took the same x86 binary? Yeah, so there's a lot of corner cases, right? What if I took the same x86 binary, ran it on an x86 machine versus a transmeta machine that's doing dynamic binary recompilation and running it on its VLIW processor underneath? You're still going to get different characteristics.
If we said that we assume that it's the same ISA, though, I mean, you really can't go into all that in 10 words. Yeah, I mean, 10 words kind of dictated what your response is.
Yeah. So, I don't know. The way that my short 10-word explanation would be something like, first of all, no. Higher IPS does not imply faster execution due to code size. The way that we're going to grade the exams, we're going to have similar things where we're going to say, please try and use fewer than this amount of words. We just want to see, do you get the key concept? You could probably even put code size, and we would be like, OK, this person gets what's going on underneath. We're not looking for a very long answer. We just want to see, do you know what is the key core feature that we're trying to test with this question? So that's why we're trying to force you to be brief, because you'll get to that point much faster. Yeah?
I have a question.
Yeah.
For exams, I heard that the exam is big enough so that we're not meant to finish it. Is that how it
Well,
works?
I wouldn't say that that's the intention. I wouldn't say that that's the intention is to make sure that you don't finish it. It is true that Professor Mutlu's exams are on the long side. We curve everything in this grade, so everything is adjusted based on the average scores. So I wouldn't worry too much about the exam length. I think that they are doable within the amount of time. If you know the answers to the questions right when you get to them, and you have to be quick with this material, right? You need to know what's going on in these machines and what's the best way to solve these questions. If you're taking a lot of time and spending a lot of time on one of the questions, it's probably best to move on these exams, because there's going to be a lot of questions for you to answer. So you want to get to the ones that you know really fast first. Save the ones that you need to think about a little bit more until the end. At least you'll get more of the questions that you could potentially get right correct. Yeah. But no, we don't design the tests to be longer than what you should be able to do. We try and make it so that if you know the answers, if you look at the question, you think for a second and you say, OK, that's right. That's what this concept was that I learned here. You write down your answer. You should be able to finish the test in time. In practice, that's really, I mean, it is a challenging test, though. OK, so that's performance metrics. Yeah?
Just going back to that real quick. Sure. But isn't it true that if you have a program that's 5 instructions, and you have 2 CPUs both running the same ISA, one of them can execute 5 instructions per second, one of them can execute 3 instructions per second, regardless of the underlying hardware or any other considerations you can imagine?
Yes.
The one that can execute 5 instructions per second will run faster. on that program.
You said 5 and 3 instructions per
Yes.
second, right? Yes, and that's what we were talking about first. If you predicate this question with if the ISAs are exactly the same, if the programs are exactly the same, if you can apply enough constraints to where this could hold. But what we wanted you to do with this question was think, OK, what are the cases where this doesn't actually hold? And the example that I just talked about was one case where this doesn't necessarily, where it kind of breaks down.
But is it enough? The ISAs are same, then you can guarantee that they run at the same time.
If the ISAs,
hardware could do a better pipelining.
yeah. So if we're dealing with a couple of things here. If you hold any one of them constant and you let the other two do anything, it doesn't really give you any guarantees on the performance. If you hold the ISA constant, as you're seeing right now, or as you will see in Lab 2, we'll probably get 38 different ways of implementing the same ISA, right? And they might have different characteristics in terms of their critical path design. Remember critical path? What's the longest latency through your system? And that might determine your clock time. So even if the ISA is exactly the same, the underlying implementation will determine what the overall performance is going to be. Yeah. OK, and so we wrapped up the homework with a performance evaluation question. Going to erase our stack. Zero address machine here. Some of it at least. OK, and for this, if we go back to the question, what we did was we gave you sort of some concrete numbers to tie back to the performance metrics question from before. So we said that you have an ISA, one ISA, that the best compiled code for this benchmark. So on a processor implementing ISA A, the best compiled code for this benchmark performs at a rate of 10 instructions per cycle. That processor has a 500 megahertz clock. On the processor implementing a different ISA, ISA B, the best compiled code for this benchmark performs at the rate of 2 instructions per cycle. That processor has a 6 megahertz clock. So the first question is, what is the performance in millions of instructions per second, MIPS, of the processor implementing ISA A? Can somebody tell me what the equation for MIPS would be? What's the general form of that equation? Yeah?
Instructions per cycle multiplied by cycles per second.
Yeah. Instructions per cycle times, let's just say, millions of cycles, because we're looking for MIPS per second. This is MIPS. OK, so if we take this definition and we plug in the numbers that we were given in the problem, let's make a little table here. So we have ISA A and ISA B. And here we have, let's do instructions per cycle. And we have millions of cycles per second. So for ISA A, we said that it executed 10 instructions per cycle. Good. For ISA B, that was 2 instructions per cycle. How many millions of instructions per second did the processor that implemented ISA A take? Well, we said it was 500 megahertz. And that corresponds to 500 million instructions per second. Same thing for the other processor, 600 megahertz, 600 million cycles per second. I might have said instructions per second for the first one. That's millions of cycles per second. Finally, if we multiply these values together, we're going to get the overall MIPS value, 5,000, 1,200. Question. What's a case where a program that runs on ISA B runs faster than the program on the machine that implements ISA A? What does that type of program look like? Let's say we start with the same source code, and I tell you, I took these two processors, I ran that program that you told me to run on both of them, and hey, the one that ran on ISA-B actually ran faster. It took less time to execute than the one on ISA-A. Well, what does that program look like on both of these machines? Is it the same? It's probably not the same, right? Yeah?
A CISC versus a RISC benefit?
Could be a CISC versus a RISC. Which one might be the CISC in this case?
The 1200 Mips.
So, yeah, so in this case, this one might have more complex logic that it needs to perform, right? It might have some more complexities that are going on inside of the machine that might take it potentially longer to execute than this one. But I don't know. I mean, the Mips machine is running a lot faster, right? So I think what you're getting at is, in order for this machine to actually take slower to execute than this one, what needs to be the case? Well, you need to have what I'm going to call a code bloat. When you compile your code, it needs to get bloated by a little bit over a factor of 4 on this machine than on this machine, right? Let's say that for every instruction I execute on this machine, I only execute 5, sorry, for every instruction that I execute here, it basically expands into 5 instructions on this machine. If I multiply 5 times this value, that's going to be greater than 5,000. And so it's going to take longer to execute the whole program on this machine versus this machine. Basically, we're getting back to that idea of, even if you know how many instructions per second can you execute, given a long enough program on one of the machines, maybe it's this machine, maybe it's this machine, you can ultimately say, OK, well, one's going to be faster than the other. Right? And actually, what I just said is actually the reverse, right? Did you catch that? It's actually the reverse of what I just said. If you have 5,000 Mips, and I apologize for that, if you have 5,000 instructions per second, that's running a lot faster on the same exact piece of code than only 1,200 millions of instructions per second. So you would need the code that runs on this machine to be a lot larger than the code that runs on this machine in order for this one to ultimately be slower. I apologize for that. Thanks for catching it. Cool. OK, any other questions on the homework, on the lab, on life? Any questions? Yeah.
So on the lab, I was just confused about loading and storing bytes and afterwards. Could you just go over the instruction in general, like what happens? And also, like, we get a virtual address, right? So we don't need to do the translation to physical address.
You don't need to do any address translation. Yeah, so that's the first thing. Now, loading bytes or half words or things like that, I'm not going to write out the full answer, but I'll give you the high-level sort of sketch that you want to think about. So if you have a machine word of data, and in general, if you want to access some sub-portion of that word, it doesn't have to be a byte. It could be 5 bits, maybe. In general, what you'll do, one technique for doing this, is to shift down the bits that you're interested in so that they're in the least significant position. So what does that look like after you do this? This will be here. This will be here. And what do you do next? You just want these bits, right? So you say, I don't want any of these. I want them to all be zeros. How do I make them all zeros? I could AND it with some sort of mask that looks like this, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. And after that, I'll be left with zeros all in here. And I'll have the value that I'm interested in over here.
But I mean, in terms of Indianness,
Yeah.
or Endianness, like, I was confused because we're using little Endian memory, right? But when we load it back in,
So So you don't need to worry about what is the endianness of memory. Remember, we're going to handle all of that in the function that we gave you. All you need to worry about is the value that we give you will be, you'll have least significant bit here, most significant bit here. It's going to be in the endianness that we specify, which is little endian for the assignment.
So
you don't have.
So when I'm loading a byte,
yeah.
Suppose I'm loading byte number 3. So it is the byte number 3 in my byte number 3 of the number I get from reading. Okay.
You don't have, again, this is one of those things where there's an interface between what's happening in memory potentially and what's happening in your processor. And the interface that we've exposed to you is this memory 32 function that just gives you how your processor would view that data that's located in memory. Okay? Any other questions? Yeah.
So we turn in the homework next week? We demo the lab next week?
Yeah, so you'll turn in the lab assignment into your hand-in folder by tonight at midnight. And then you can demo it during one of the labs next week, whichever one works for you. Yeah.
Can we do the demo during office hour?
I think I'd prefer, at least, I think we'd prefer to do it during lab. I don't think there's any reason why not. Like, if it's hard for you to make one of the lab sections and the office hours are easier, feel free to go to one of the office hours.
How long is the demo going to be usually?
So I think it's up to the TAs. What I've basically been, what I'm concerned about is, can you explain roughly what's going on in your simulator? Can you give me some feel for how you tested it? And that's good, right? Okay, thanks everyone. Yeah. Yes, you can demo it today during today's lab session, which is from